Hello friends, welcome back to my YouTube channel. In this video, I will continue my discussion on high pressure vessels and theories of elastic failure. Today, I'll be talking about the maximum shear stress theory. In my previous video, I had discussed maximum principal stress theory, and today I'll be talking about the maximum shear stress. So let us begin the discussion. The design of high pressure vessels, as you know, it is based on the theories of elastic failure. Now, what is elastic failure? Elastic failure in a material occurs when it is subjected to a load that exceeds its elastic limit. Now, what is this elastic limit? Beyond its elastic limit, the material is going to get permanently deformed or permanently ruptured. So there are many theories that have been proposed in the literature to account for this elastic failure. And we call these theories as the theories of elastic failure. Important theories of elastic failures. You have maximum principal stress theory. I have discussed this in my previous video. Then you have maximum shear stress theory. Today we are going to talk about this theory, maximum shear stress theory. Then you have maximum strain theory, maximum strain energy theory. Today we will be talking about the maximum shear stress theory. Okay. So as the design of high pressure vessels, it is based on theories of elastic failure. It is important for us to know more about this theories of elastic failure. So elastic failure in a material, it will occur if the material is subjected to a load that is more than its elastic limit. So beyond the elastic limit, the material will be getting permanently deformed or permanently ruptured. And to account for this failure, to account for this elastic failure, many theories have been proposed in the literature. We call those theories as theories of elastic failure. I have listed important such theories. Maximum principal stress theory, last time I discussed it. Then maximum shear stress theory, today I will be discussing it. Then in my coming videos, I will be talking about maximum strain theory and then maximum strain energy theory. So let us talk about the maximum shear stress theory. According to this theory, failure in a material will occur if the maximum shear stress induced in the material, it becomes equal to the shear stress that would be set up in the material at the elastic limit. And in this case, the elastic limit is taken as the yield point of the material, the point beyond which there will be plastic deformation in the material. Okay. Now, what is the maximum shear stress? Maximum shear stress, if you neglect the effect of the axial or longitudinal stress, that is sigma A, then the maximum shear stress is given by this equation. What is that equation? Sigma S max is equal to sigma C minus sigma R upon 2. What is sigma C? Sigma C in this case is the circumferential stress and sigma R is the radial stress. And these stresses will be evaluated at the inner surface of a cylindrical vessel, that is at the inner diameter. And for almost all high pressure vessels, external pressure is 0. So when these two stresses, that is sigma C and sigma R, they are evaluated at the inner surface, and when external pressure is 0, we will be using those stresses in this equation to get the maximum shear stress. And as per this theory, when this maximum shear stress becomes equal to the shear stress at the elastic limit, then material is going to fail. Then what is the yield point? As I said, this is a point on the stress strain diagram where the elastic behavior of the material will end and the plastic behavior will start. So what is the stress strain diagram, let me tell you. So you have stress plotted against strain, that is sigma plotted against epsilon. So epsilon. So you till the elastic limit, this graph will be a straight line. Then you will reach a point which we called the yield point, after which the graph will no longer be a straight line, or rather it will be a curve which indicates plastic behavior in the material. That means the material after this point, the material will not regain its original shape and size even if you remove the applied load. Whereas below this point, the material will regain its shape and size after you remove the applied load. So this is the yield point. Beyond this yield point, the material is going to behave plastically. So we are talking about the shear stress that is induced in the material. If it becomes equal to the shear stress corresponding to this point, the material is going to fail as per this theory. I hope this is clear to you. Next. Okay. We just got the equation. We are using the equation. We are not deriving it. We are directly taking it. The maximum shear stress is sigma S max is equal to sigma C minus sigma R upon 2. And the sigma C and sigma R, they are evaluated at the inner surface, that is D is equal to Di, and when external pressure is 0. So you have this equation for sigma C, Pi Di square minus Po Do square divided by Do square minus Di square plus Do square into Di square upon D square into Pi minus P naught divided by Do square minus Di square. So this is the equation for circumferential stress. I have derived it in my previous, one of my previous videos. I am giving link to that video in the description section. So this equation is written by considering the sign convention. What is the sign convention? Tensile stress is compressive and tensile stress is taken to be positive and compressive stress is taken to be negative. Sigma R, equation for sigma R, that is radial stress, is Pi Di square minus Po Do square divided by Do square minus Di square minus Do square into Di square by D square into Pi minus P naught Do square minus Di square. Okay. So when we say that we are going to evaluate this at the inner surface, that means wherever there is D in the equation, we are going to replace it with Di. And wherever there is P naught, we are going to equate it to 0. So accordingly, in case of sigma C, it will be Pi Di square minus Po is 0. So minus 0 into Do square divided by Do square minus Di square plus Do square into Di square by Di square. Now D square is replaced with Di square into Pi minus P naught is 0. So Pi minus 0 divided by Do square minus Di square. That is sigma C is equal to Pi Di square upon Do square minus Di square plus Do square, because Di square will get cancelled, plus Do square into Pi upon Do square minus Di square. So in the next step you can take Pi common, or before that for sigma R, the equation will be Pi Di square minus 0 into Do square, Po is 0, divided by Do square minus Di square minus Do square into Di square by Di square, D replaced with Di into Pi minus P naught is 0. So Pi minus 0 divided by Do square minus Di square. So that gives us sigma R as Pi Di square divided by Do square minus Di square minus Do square upon into Pi divided by Do square minus Di square. So if you use these equations, you'll be getting this equation. Sigma S max is equal to 1 by 2 into Pi Di square divided by Do square minus Di square plus Do square into Pi upon Do square minus Di square minus Pi Di square upon Do square minus Di square plus Do square into Pi upon Do square minus Di square. So we have just used the equations for sigma C and sigma R in the equation for sigma max. Now let us continue with this equation. So we just got this equation for the maximum shear stress. Sigma S max is equal to 1 by 2 into pi di square upon do square minus di square plus do square into pi upon do square minus di square minus pi di square upon do square minus di square plus do square into pi upon do square minus di square. Okay, so that will give us sigma S max as 1 by 2 into 2 times of do square into pi upon do square minus di square. Why? Because the first term pi di square divided by do square minus di square will get cancelled out with this. Let me do it. So this minus this, and you have addition of the same two terms, that is do square into pi upon do square minus di square. So that's why you get sigma S max as 1 by 2 into 2 do square into pi upon do square minus di square. That is sigma S max is equal to do square into pi upon do square minus di square, because 2 that will get cancelled out and you are left with do square into pi upon do square minus di square. So this is the induced stress at failure according to the shear stress theory. So this is the maximum shear stress that will be induced in the material, and if this becomes equal to the shear stress at the yield point, then the material is going to fail. So this is the maximum induced shear stress, and if this is equal to the shear stress at the yield point, the material is going to fail. So this is numerically equal to half of the yield stress in simple tension. Okay, so what is the concept? You have the equation. We got the equation for sigma max, and this is numerically equal to 1/2 of the yield stress in simple tension at the elastic limit. That is 1/2 of the yield stress in simple tension at the elastic limit. So the equation is, we got this sigma S max is equal to do square into pi upon do square minus di square. So this is the induced shear stress at failure according to the maximum shear stress theory, and this is numerically equal to half of the yield stress in simple tension at the elastic limit. If the material is subjected to simple tension, and when the elastic limit is reached, then whatever is the value of yield stress, half of that is the maximum shear stress that is induced. So mathematically you can simply write this as sigma S max is equal to sigma y upon 2, where sigma y is the yield stress. Sigma y is the yield stress in simple tension. So that is sigma y upon 2 is equal to do square into pi upon do square minus di square. But according to Manning, for high pressure cylindrical vessels, it is not sigma y upon 2, but it is actually sigma y upon root 3. So according to Manning, for high pressure cylindrical vessels, if sigma maximum shear stress is equal to 1 by root 3 into sigma y, that is the yield stress in simple tension at the elastic limit, then the material is going to fail. Again, we are going to continue with this equation. So that means sigma y upon root 3 is equal to do square into pi upon do square minus di square. So this is more correct equation, correct relation between the maximum shear stress and the yield stress at the elastic limit. So that's why we are going to continue with this. So therefore this will be sigma y upon root 3 is equal to do square into pi upon do square minus di square. That is sigma y is equal to root 3 into do square into pi upon do square minus di. And we just got this equation. Let us continue with it. Sigma y is equal to under root of 3 do square into pi upon do square minus di square. Now, let us get the design equation, which we can use to find out the diameter of inner and outer diameter of the vessel and thickness of the vessel. So, for that, we are going to use a factor of safety, that is Fs. Why we are using it? We are using it so that the induced stress will be less than the yield stress. So that is why you have sigma y upon Fs is equal to, that is, we are using a lower value of sigma y, the yield stress. Therefore, it will be sigma y upon Fs is equal to under root of 3 into do square pi upon do square minus di square. That is, sigma y upon Fs is equal to root 3 into do square upon di square into pi upon do square upon di square minus di square upon di square. So that is what I have done. I have taken di square common from the denominator, and if I do that, you get this. It will be do square upon di square into pi upon do square upon di square minus di square upon di square. So in the next step, di square upon di square is 1, and for do, for the ratio do upon di, we are going to use k to represent that ratio. So it will be sigma y upon Fs is equal to under root of 3 into k square into pi upon k square minus 1, where we have replaced du upon di with k. That is, sigma y upon Fs is equal to, we will simplify it, we'll bring k square minus 1 on this side. So it will be sigma y upon Fs into k square minus 1, that is equal to root 3 into k square into pi. So if you simplify this further, we will get sigma y upon Fs into k square minus sigma y upon Fs is equal to under root of 3 k square pi. Then we will collect k square terms on one side. So that will give us sigma y upon Fs into k square minus root 3 k square pi. That is equal to sigma y upon ps. So I have brought this term on this side and taken this term to the other side. Okay, so let us continue. The design equation. So far we got this. Sigma y upon Fs into k square minus root 3 into k square into pi, that is equal to sigma y upon Fs. That is, in the next step, k square will be taken out as a common term. So this will be k square into sigma y upon Fs minus root 3 into pi, that is equal to sigma y upon Fs. That is, k square is equal to sigma y upon Fs divided by sigma y upon Fs minus root 3 into pi. Let us simplify it further. Therefore, k square will be equal to sigma y upon Fs divided by sigma y minus root 3 pi into Fs divided by Fs. So in the next step, Fs will get cancelled out. So you are left with k square is equal to sigma y upon sigma y minus under root of 3 into pi into Fs. That is, k will be sigma y upon sigma y minus under root of 3 into pi into Fs raised to 1 by 2. So this equation, sigma y will be known to us, pi will be known to us, Fs will be known to us. So you can use all the known values to get the value of k. You are getting k, that means you are getting the value of ratio of outer diameter to inner diameter. So by knowing this, you can find out these diameters, outer diameter and inner diameter, and then you can also find out the thickness of the vessel. So this is the design equation to get the thickness of high pressure vessels according to maximum shear stress theory. So with this, I end my discussion for today. I end my discussion for maximum shear stress theory. I hope you have understood what is the theory and what is the design equation according to this theory. So thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In my next video, I'll be talking about the third theory of elastic failure, that is maximum strain theory. I hope you'll join me in my next video. For now, Thanks. Have a nice day. Bye bye.